Hi, this is Mrs. LaBarbera. This is AP Physics Mechanics C. Today's topic is describing simple harmonic motion part 1. The objectives are: know the general behavior of a spring mass system in simple harmonic motion in qualitative terms. Know the terms that describe simple harmonic motion and the relationship between each term. Understand the simple harmonic motion is projection of uniform circular motion onto a diameter. Be able to describe the displacement in relation to time for a mass spring system in simple harmonic motion. Be able to determine the amplitude, period frequency, or angular frequency with a given graph. The course of oscillations. A body that undergoes oscillation always has a stable equilibrium position. The body is oscillating because there is a restoring force that always pulls it back to this equilibrium position when the body is moving away. Take a look at this two animation. The equilibrium is right in the middle. So when the body is going to the right, the force is to the left. When the body is to the left, the force is to the right. Over here is the same way. This dotted line is the equilibrium. When the body is up, there's a force pushing it down, pull it down. When the body is down, there's a force pushing it up. Always trying to push it toward the equilibrium position. Because the force is restoring, the force and displacement are in the opposite direction. Hence the acceleration and the displacement are always in the opposite direction. This is because acceleration and the net force are always in the same direction, according to Newton's second law. Simple harmonic motion is a special case of oscillation, when the restoring force Fx is directly proportional to the displacement from equilibrium. Since F equals ma, that means acceleration is also directly proportional to displacement. We know a motion is simple harmonic motion if A is proportional to negative x. Here is a box vibrating on a spring is simple harmonic motion because the force acting on the box equals to negative kx. This is Hooke's law. So F is proportional to negative x. A is also proportional to negative x. Here are the force diagram on the box. When the box is stretched, the displacement is greater than 0, but the force is less than 0, and the acceleration is less than 0. Here is the free body diagram. No more force, gravity cancels. The net force is the force from the spring. This force is to the left is opposite to the displacement. When the body is at equilibrium position, there is no force because the spring is relaxed. There is no force from the spring, and the glider has no acceleration. The two forces, normal force and the mg, cancels out with each other. When the spring is compressed, the displacement is less than 0, but the force and acceleration are going to the right, so they are greater than 0. A body vibrates back and forth as shown. For each of the following values for the body's velocity and acceleration, state whether its displacement is positive, negative, or 0. So we know for simple harmonic motion, x is proportional to negative x. If we know the direction of ax, we can know the direction of x regardless which way it's going. So I hope you know how to answer this question, and these are the answers. Describing simple harmonic motion. Simple harmonic motion is projection of uniform circular motion onto a diameter. So this red ball is uniform circular motion. This blue ball is the projection. The blue ball is the shadow that moves back in simple harmonic motion, right? Simple harmonic motion is projection of uniform circular motion in one dimension. In this case, it's projected in the y dimension. How do we find the displacement equation? We know the circular motion pretty well. So again, let's take a look at this circle. This circle is called a reference circle. This OQ called phasor. So this shadow, the black dot, corresponding to the simple harmonic motion in the horizontal. The ball moves in uniform circular motion. The shadow moves back and forth on the x-axis in simple harmonic motion. So this is just geometry. If we know the hypotenuse, we know the angle, we can find adjacent. In this case, adjacent is the x. Displacement equals a cosine theta. X equals a cosine theta. But theta is a function of time. Since the motion is uniform, alpha equals 0, so theta equals theta naught plus omega t. Omega is constant. But let's suppose at t equals 0, you didn't start from 0. You start from an angle phi. Start from here. Then the general equation would be x equals a cosine omega t plus phi. Suppose at t equals 0, you didn't start from 0. That's a general equation. So let's take a look at special cases of phi. Suppose at t equals 0, phi equals 0. So where are you? You are right over here. That's t equals 0, right over here. In that case, the equation is simplified as x equals a cosine omega t. Suppose at t equals 0, phi equals to pi over 2. So corresponding to a circle, you are over here. You're moving to the left. In that case, this equation can be simplified as negative a sine omega t. If at t equals 0, you start from all the way from the left here, then your equation will become negative a cosine omega t. X naught becomes negative a. Or in another case, you can start from here on the bottom. Your phi is negative pi over 2. Moving to the right. In that case, again, your x naught equals 0, just like when phi equals pi over 2. But you're moving to the right, so the equation for x is simplified as a sine omega t. As you can see, x can be sine or cosine. It's a sinusoidal function. So it doesn't matter if it's sine, cosine, essentially they are the same function. So what is it? It depends on your initial angle phi. Okay, so there are different ways to find phi. If the phi is above, if this bow is above the x-axis, we say that phi is positive. If it's below the x-axis, we say that phi is negative. When phi is negative, it really means the box is going to the right. When phi is positive, means it's going to the left. Displacement is a sinusoidal wave. Let's take a look at this. This is the simple harmonic motion for object vibrating on a spring. Its displacement is just a sine function. It can be represented as sine or cosine. It's just with a phase difference. Xt graph for different phase phi. So in this equation, the angle phi is called phase angle. It tells us at what point in the circle the motion was at t equals 0. It's equivalent to where around the circle the point Q was at t equals 0. If we let x equals x0 when t equals 0, then x0 or x naught equals a cosine phi. We know when phi is not 0 or phi is not equal to pi, that x0 has to be less than a. So special cases, when phi equals 0, we talked about it. This is where you start. In this case, x naught equals to a, you start from your longest displacement, right? Biggest displacement. If phi equals to pi, you're starting at left at your biggest displacement. If phi equals to positive or negative pi over 2, somewhere in the middle, it's exactly in the middle. X naught equals to 0, but it can be moved to the left or right. If phi equals to positive pi over 2, it's going to the left. If phi equals to negative pi over 2, it's going to the right. So here are the xt graph. It's a sine function or cosine function. It's just shift, right? Special case, when phi equals 0, remember this is just cosine omega t. So this is cosine function. Here is phi equals to pi over 2. Phi equals to pi over 2, you shift pi over 4. You shift pi over 4 to the right. So the other ones is phi equals to negative pi over 2 or phi equals to positive pi over 2. Negative pi over 2 is a sine, positive sine function. When phi equals to pi over 2, it's negative sine function because you're going to the left. And this green one is you're going to the right. So these four curves show simple harmonic motion with the same period t and amplitude a, but with different phase angle. Let's take a look at this example. A glider is attached to a spring. If the glider is moved to x equals to 0.1 meter and released at a time t equals 0, it will oscillate with amplitude a equals 0.1 and the phase phi equals 0. Suppose instead at t equals 0, the glider is at 0.1, but it's moving to the right. In this situation, is the amplitude greater than, less than, or equals to 0.1? Okay, let's take a look. What does that mean when it's moving to the right? It's moving to the right, has to be moving to the right here. And it's moving, and its position is at 0.1, so maybe it's over here, right? Somewhere over here. So is the amplitude greater than or less than 0.1? Amplitude is here, so amplitude is greater than 0.1. Is the phase angle greater than or less than or equals to 0? Phase is below here, below the horizontal because it's going to the right. So it has to be less than 0. Suppose instead at t equals 0, the glider is at 0.1, but it's moving to the left. The moving to the left has to be above 0. So maybe over here. Over here. So is amplitude greater than, less than, or equal to? It has to be still greater. Amplitude over here is greater than here, right? Is the phase angle greater, less than, or equal to 0? The phase angle is above x-axis, so it has to be greater than 0. Terms describing simple harmonic motion. So simple harmonic motion is sinusoidal waves. So let's use the simplest one. Let's use cosine, right? First note is amplitude. That's a maximum magnitude of displacement from equilibrium, from the middle line to the very top, or from the middle to the very bottom. A cycle is one complete round trip. So from over here and coming back, that's round trip. Right? Round trip is from here to here. That's a round trip. Period is the time for one cycle. It is always positive. Its SI unit is second. Period is time from here to here is one cycle. The time from here and back to here. Or from the middle. Here is and coming right back. Okay? Whoops. That's so from the middle, one cycle is, that's one cycle. Start, that's one cycle. Okay, frequency is the number of cycles in unit of time. It is also positive. Its SI unit is hertz, so 1 hertz equals to 1/second. What is angular frequency? Angular frequency is the number of radians in a unit of time. Frequency, think about it, this one cycle corresponding one circle. So frequency is how many circles it's going in a second. So angular frequency is asking how many radians it's going in 1 second. We know one circle has 2 pi radians, so angular frequency is just 2 pi times f, right? Its unit is radians per second. And angular frequency, since it's how many radians per second, it's the same as angular velocity, how many radians it goes per second. So the relationship between frequency and the period is this. Frequency equals 1 over period, period equals 1 over frequency, and the relationship between omega ft is this. Okay? Example, let's take a look. So here is a graph. What is amplitude? What is the period? What's the frequency? What's the angular frequency? Amplitude is from middle to the highest, or the middle from lowest. So I hope you can figure it out. Period is the time for one cycle. From here to here is exactly one cycle. That's 16 seconds. Frequency is 1 over period. Angular frequency equals to 2 pi f. That's it. Another example, object on a horizontal frictionless surface is attached to a spring, just like this, and then released, it will oscillate. If released, it will oscillate. If it is displaced at a distance 0.13 meters from its equilibrium position, released with 0 speed, then after time 0.78 seconds, it's over here. And its displacement is found to be 0.13 meters on the opposite side, and it has passed equilibrium just one time. Find amplitude. Amplitude is the maximum displacement from equilibrium, so amplitude has to be 0.13. Period from here to here is 0.78, so that's half a cycle. So the period is double of this time, and frequency is just 1 over period. And that's it. I hope that helps. Thanks for watching.